Okay, so the next example, let f of x equals, or let me, I can include it as part C of the previous example. Previous example, we were asking, determine the intervals on which a given function is increasing and the intervals on which the given function is decreasing. Now let's say for the function given in part C, f of x equals 3x to the power 4 plus 4x cubed minus 12x squared plus 2. Again, to determine intervals of increasing, decreasing, find f prime of x and solve for f prime of x equals 0 and use the sign chart. So what is f prime of x? What is the derivative of this given function? Derivative of 3x to the power 4 is 12x cubed. Then the next term derivative is 12x squared minus 24x. I can factor 12x out, then what will be left? X squared plus x minus 2. And I can factorize this as 12x times x plus 2 times x minus 1. Now solve for f prime of x equals 0. Then what do we get? We get 12x times x plus 2 times x minus 1 equals 0. So that gives x equals 0, x equals minus 2, and x equals 1. So I can draw the sign chart. So we said that in the first row in the sign chart, you locate the x values. Now, which x values should I specify here? The zeros of f prime, the roots of f prime, solutions of f prime of x equals 0. What are they? 0, minus 2, and 1. So please remember that you have to specify these points in the order. So which one is the smallest one, and then the next one, and so on. So the smallest one here is minus 2, then we have 0, then we have 1. And then in the next row, I write f primes, the sign of f prime, and then f, whether f is increasing or decreasing. So f prime, I know that it's 0 on these 3 points, because how did I come up with these 3 points? I came up with these 3 points because they were zeros of f prime, meaning that f prime of x becomes 0 at these 3 points. Now I have to see whether f prime is positive or negative at each of these points. So this region here, this region corresponds to the x values less than minus 2. So if x is less than minus 2, we can use a test point, for example, right? Just use, for example, x equals minus 3. So test point x equals, let's say, minus 3, less than minus 2. Then let's see, let's find f prime of minus 3. Let's see how much it is. F prime of minus 3, if x is minus 3, this is the formula for f prime of x. 12x times x plus 2 times x minus 1. If x is minus 3, 12 times minus 3 is minus 36 times x plus 2 means times minus 3 plus 2 times minus 3 minus 1. How much is that going to be? So 36 times minus 4, which is negative. So negative here, and therefore we will have positive here, negative here, positive here. The signs change alternately at the roots unless there are repeated roots. But here, everything is single root. The multiplicity is 1. They're all single roots because there is no power. Power is 1, power is 1, power is 1. So everything is single root here. And that's why we change the signs alternately here in the sign chart. That's all single roots. There's no repeated root here. So f prime negative, then less than -2, between -2 to 0 positive, between 0 to -1 negative, and after 1 again positive. So of course, if you don't want to use this method, changing the sign alternately, you can use another test point between -2 and 0, and you can see that the sign will be positive. For example, you could use -1, which is a number between -2 to 0. Find f prime of -1, you will see it's positive. Or same thing for other regions between 0 and 1. You could use a test point such as 0.1, or the region after 1, you can use a test point such as 4, and so on. So f prime, so we have all the signs for f prime, where it's negative, where it's positive. So we can say that f is decreasing on this region, then increasing, decreasing, and increasing. Based on the theorem, and again, because the function is a polynomial, therefore continuous and differentiable everywhere. So we can apply the theorem and say that, so based on theorem above, and again, because f is continuous and differentiable everywhere, let me not repeat this again. I have mentioned in previous parts. We can say that f is increasing on which intervals? On -2 to 0. And what else? 1 to infinity. And f is decreasing on which intervals? -infinity to -2. And what else? Also between 0 and 1, and 0 and 1, and 0 and 1. Okay, now let's look at the next concept called concavity. So let's see when can we say that a function is concave up, and when can we say that the function is concave downward. So definition, let f of x be a function with, let's say, domain a to b. We say that f of x is concave upward if every secant line connecting 2 points of the graph of f of x lies entirely above the graph. See? Look at this picture. Concave upward. Concave upward means something like x squared. You can always think about x squared or a parabola opening upward as a graph which is concave upward. When do we say that a function is concave upward? If every secant line, every segment every line segment connecting 2 points of the graph lies entirely above the graph. Look at the red one, red line segment here. It connects 2 points of the graph, this point and this point, right? It connects this point to this point of the graph, and it lies entirely above the graph. See, this line is entirely above the graph because the graph, look at the graph, is entirely below this line, red line segment. Or for this one, the blue one, it connects again 2 points of the graph, this point and this point here. And it lies entirely above the graph. The graph is entirely below this. But in this case, we, we say that the function is concave upward. Similar definition for concave downward. Similarly, we say that f of x is concave downward if every, again, secant line connecting 2 points of the graph lies entirely below the graph. See, if you have a picture like this, now if I connect any 2 points of this graph, like these 2 points, or again, like these 2 points, for example, see again, whether it's the red line segment or blue line segment, in any case, if the function is concave downward like this, in any case, the line segment will lie entirely below the graph. The graph is, see, look at here, the graph is entirely above the blue line segment, and here, again, the graph is entirely above the red line segment. Okay, so this is a definition of concavity. See, the definition itself is independent of derivatives. There is no derivative appeared in the definition. The only thing that is appeared, the only concept that is appeared is the line segment. Line segment connecting 2 points of the graph, which should either lie entirely above or below the graph, depending on whether the function is concave up or down. But there is no mentioning of derivatives here in the definition. Similar to increasing, decreasing function. For increasing, decreasing function as well, in the definition, we didn't have any derivatives appeared. But then we saw a connection between derivatives and increasing, decreasing function. Same thing here. So in the definition, there is no mentioning of derivatives, but there is a connection between concavity and derivatives. So what is the connection with derivatives? So suppose that, so again, part A, suppose that f of x is a function which is twice differentiable on some interval a and b, and assume that f double prime of x is bigger than 0 on a and b, then f of x is concave upward on a and b. Similarly, for part B, suppose that f of x is twice differentiable on A and B, and assume that f double prime of x is less than 0 on A and B, then f of x is concave downward on A and B. Okay, so second derivative being positive implies concave upward. Second derivative being negative implies concave downward. So before giving the examples, one definition, x equals a is called an inflection point for f of x if concavity changes at x equals a. So either from upward to downward, or from downward to upward. Okay, so inflection point means the point where concavity changes from upward to downward or from downward to upward. Now let's look at an example. Let's start with the simplest example for concavity. F of x equals x squared on minus infinity to infinity is concave upward. Right? You know how the graph looks like, of course, for f of x equals x squared, the parabola, and it's concave upward. How can we verify this? Using the second derivative. Since f prime of x is 2x, so f double prime of x, the second derivative means the derivative of the first derivative, and that's going to be 2, which is positive for every x in minus infinity to infinity, and that means f of x is concave upward on this whole interval minus infinity to infinity. And similarly, you can show that, or exercise show that f of x equals minus x squared is concave downward on minus infinity to infinity, right? So minus x squared, it looks like this, and it's always concave downward. You can again verify this using second derivative. You will easily show that the second derivative for this function is minus 2, which is always negative. So why do I say always negative? Because when you say minus 2 means a constant function, right? So constant function is a function whose output is independent of the input. So no matter what x value you use, the output is minus 2. So I can say that for every x, the output is negative because the output is independent of the input. So for every x, the output is minus 2, and minus 2 always, of course, is negative. And therefore, the function is concave downward according to the theorem we just learned. Okay, so next example. Find the intervals at which f of x is concave upward. And the intervals at which f of x is concave downward. And find the inflection points. Find the inflection points, if there is any. Some functions may not have inflection points. For example, see, this function x squared was always concave upward, so it does not have any inflection point. Remember, inflection point means a point where concavity changes. If the concavity is always concave upward or always concave downward like this one, well, there is no inflection point. So let's start with f of x equals x cubed. So this one, f prime of x is 3x squared. And therefore, f double prime of x, the derivative of first derivative, is 6x. Now, when can I say that f double prime is positive, and when can I say f double prime is negative? So next, solve for f double prime of x equals 0 to determine concavity. Okay, so if I want to summarize what we are learning today, is that for increasing, decreasing, to determine increasing, decreasing, we have to solve for f prime of x equals 0, find the roots, and then use the sign chart for f prime. To determine concavity, whether concave upward or concave downward, we have to solve for f double prime of x equals 0, find the roots of f double prime, and then use the sign chart for f double prime. Okay, so please remember, increasing, decreasing related to f prime, whether it's positive or negative. Concave upward, concave downward is related to f double prime, whether f double prime is positive or negative. Here the question asks about concavity. So let me solve for f double prime of x equals 0. What are the roots? So it's very easy to solve in this case. 6x equals 0. That gives x equals 0. Then I use the sign chart. Sign chart for f double prime of x. To determine concavity. Okay, here you are. This is the sign chart, x values. So we said that on the first row for the x values, we have to specify the roots of, well, here f double prime. In the previous examples, because we were determining increasing, decreasing, the first row we were determining, specifying the roots of f prime. But here related to concavity, we need to specify roots of f double prime. And then f double prime. And then f. So 0, as we said here, it's the 0 of f double prime. Before it, you can use a test point, for example, -1. F double prime of x, let's say 6x. 6x at -1 is -6, right? So I can say negative here and then positive here. Sign change alternately because we don't have a repeated root, or we could also use test point. 6x at x equals 1, for example, is 6 times 1, which is 6, which is positive. So f double prime is negative before 0, positive after 0. So negative means concave downward, and F double prime positive means concave upward. See, when we draw this sign, we mean F is concave downward. When we draw this sign, we mean F is concave upward on this interval. So F is concave downward on which interval? Before 0, right? So minus infinity to 0. And F is concave upward after 0. After 0, F double prime positive, F is concave upward. So on 0 to infinity. And we know that the graph looks like this, right? See, before 0, this part, this graph looks like minus x squared, right? This looks like minus x squared before 0. After 0, this part looks like x squared. So if a graph looks like x squared, means it's concave upward. And if a graph looks like minus x squared, means it's concave downward. So concave downward before 0, concave upward after 0. And our calculation verifies this as well. And the inflection point at x equals 0, because concavity changes at x equals 0. All right, let's look at the next example. F of x equals, let me consider the function that we previously studied to determine increasing, decreasing function, the increasing, decreasing interval. This function here, 3x to the power 4, 4x to the power 3, minus 12x squared plus 2. 3 x to the power 4, 4x to the power 3, minus 12x squared plus 2. Okay, so we already determined intervals of increasing, decreasing for this function. Now in this question, we want to determine intervals of concavity, and which interval is concave upward, and which interval concave downward, and find the inflection points. So first we need f double prime of x. And to find f double prime of x, of course, first I need f prime of x. What is f prime of x? F prime of x is 12x cubed plus 12x squared minus 24x. So f double prime of x, which means the derivative of the first derivative, is going to be 36x squared plus 24x minus 24. So then next, solve for f double prime of x equals 0. So that means 36x to the power 2 plus 24x squared minus 24 equals 0. I can factor 12 out. 3x squared plus, so 24x here, plus 2x minus 2 equals 0. So that means 3x squared plus 2x minus 2 equals 0. Okay, so what are the values for x? I can use the quadratic formula. X equals minus 2 plus minus root 4 minus b squared minus 4ac, minus b plus minus root b squared minus 4ac. So 4 minus 4 times 3 times minus 2 divided by 2a, so divided by 6. And then that's -2 plus minus. So 24 plus 4 is 28. Root 28 divided by 6. Okay, so I have two roots. Now let me use the sign chart, then use the sign chart for f double prime. So how did we say we have to use the sign chart? So the first row, in the first row, you have to specify the roots of f double prime. F double prime equals 0 at which points? At 2 points, -2 minus root 28 over 6 and -2 plus root 28 over 6. So -2 minus root 28 over 6. Please remember that you have to specify these points in the order. Which one is the smaller? Of course, -2 minus root 28 over 6. And which one is the bigger one? -2 plus root 28 over 6. And then f double prime here. And then f here. So zeros here, f double prime will be, of course, 0 at these 2 points. Now, for f double prime on this region means minus infinity to this point. I want to know whether f double prime is positive or negative. Well, we can use a test point. So what should I use as a test point? Well, let's just have some estimate, rough estimate for this. Root 28 is 5 point something, right? -2 minus 5 point something is -7 point something divided by 6 is -1 point something. So let me use, just to be safe, let me use, for example, -3. -3 for sure is less than this number, right? This number is around -1 point something, -3 for sure is less than this number. So -3 lies in this region. So I can use it as the test point. So test point, let's say x equals -3. Then let's find f double prime of -3. Let's see whether it's positive or negative. F double prime is this, 36. 36 times -3 squared plus 24x. So plus 24 times -3 and -24. This is 36 times 9 -3 times 24. -24 means -4 times 24. And of course, 9 times 36 is bigger than 4 times 24. So this number is positive, this number negative. So, but this, the first number is bigger in absolute value. So the whole number will be positive, or you can of course use calculator just to verify that this whole number is positive. But even without calculator, it's obvious that the final result must be positive. So please remember, when we use sign chart, we don't care about the values. We just care about the sign, whether it's positive or negative. So f double prime is positive on the first region, this region positive, because of the test point that I used here. This test point here is less than this number, -2 minus root 28 over 6. So positive here, and the signs will change alternately. Again, see, we don't have any repeated root, so signs change alternately. So plus here, sorry, minus here, plus here. And then, so here we had concave up, concave down, concave up. So F is concave upward. On which intervals? Before this number, minus infinity, -2 minus root 28 over 6. and concave upward on after this root minus 2 plus. So minus 2 plus root 28 over 6 to infinity. And f is concave downward between these two numbers, right? Negative f double prime is negative here, which means between these two numbers, minus 2 minus root 28 over 6 and minus 2 plus root 28 over 6. And what about the inflection points? Point or points? Inflection points. In this case, there are more than one. There's more than one inflection points. X equals minus 2 minus root 28 over 6. And x equals minus 2 plus root 28 over 6, because at both of these 2 points, concavity changes, right? At this point, concavity changes from up to down, and at this point, concavity changes from down to up. Concavity changes at these 2 points. All right, so let's look at the next example. Let f of x equals x e to power x. Find the intervals of increasing, decreasing. And intervals of concave up or down for this function. So this is a good example to summarize what we learned today. For increasing, decreasing, we need f prime, and we need to know whether it's positive, where it's positive, where it's negative. For concave up, down, we need f double prime, and we need to know where it is positive and where it's negative. So for first part, we have to find f prime of x. How can I find f prime of x? Well, f of x is the product of two functions. So to find derivative of this function, I need the product rule. Product rule, uv derivative is u prime v plus uv prime. So x derivative times e to the x plus x times e to the x derivative. Derivative of x is 1, so e to the x plus x e to the x. And I can take e to the x out as a common factor, and 1 plus x will be left. Okay. Then we need the roots of f prime, right? Because we need the sign chart for f prime to determine intervals of increasing, decreasing. And for the sign chart, we need the roots of f prime, where f prime becomes 0. And based on that, then we can determine where f prime is positive and where f prime is negative. So then solve for f prime of x equals 0. So that gives e to the x times 1 plus x equals 0. So that means e to the x, because e to the x is always positive. Remember, exponentials are always positive, strictly positive. So they can never be 0. They can never be negative. They're always strictly positive. Now here I have products of two numbers equals 0. One of them is an exponential, so it's always positive and therefore non-zero. So that means the other factor must be 0. So the other factor, which is 1 plus x, must be 0. And that gives x equals -1. So that's the only root for f prime. Then I use the sign chart. For f prime of x to determine intervals of increasing, decreasing. So there you are. This is a sign chart. The first row, I have to specify the x values. Which x values? The roots for f prime. The roots for f prime, there's only one here, -1. There you are, -1. And then in the next row, I will write down f prime, the next row f itself. And I know that f prime becomes 0 here because how did I find -1? -1 was the root of f prime, which means the x value at which f prime becomes 0. So I can write down 0 here. And before -1, this region, before -1, I can use a test point. Let's say -2, for example. Test point x equals -2 less than -1. So f prime of -2 will be e to power -2. Look at the formula for f prime of x. E to the x times 1 plus x. So e to the -2 times 1 minus 2, and this is negative, right? Because 1 minus 2 is -1, and e to any power is always positive. Positive times negative is negative. So negative here and positive here, sign change alternately because this is not a repeated root. And f prime is negative here. F prime negative means f is decreasing. And here f prime is positive. F prime positive means f is increasing. So f is decreasing on -infinity to -1. F is increasing on -1 to infinity. By theorem above, since f is continuous and differentiable everywhere, we are allowed to apply the theorem. Remember the theorem that enabled us to determine increasing, decreasing functions based on the derivative, sign of derivative. The condition was that f must be continuous on the closed interval, differential on the open interval. But here we have a function which is always continuous and differentiable because exponentials are always continuous and differentiable, polynomials as well. Product of them will be also continuous and differentiable everywhere. Okay, so f is decreasing on this interval, increasing on this interval. I can say it's a by theorem. I can say because of theorem above, or here I can say note, just to be more clear. So I concluded these two because of the theorem that we learned today, and we were allowed to use the theorem because f is continuous and differentiable everywhere. Not f. So we are allowed to apply the theorem. Okay, so this is for intervals of increasing, decreasing. Now the other part of the question asks us to determine intervals of concave up and down. So let's do that as well. For second part, we need f double prime of x. F double prime of x means what? Means derivative of first derivative. First derivative was e to the x times 1 plus x. So derivative of e to the x times 1 plus x. Again, I have to use product rule. So that gives e to the x derivative times 1 plus x plus e to the x times 1 plus x derivative. So that's going to be e to the x times 1 plus x. Derivative of 1 plus x is 1, so plus e to the x. Again, I can take e to the x out as a common factor. What will be left? 1 plus x plus 1. So that's e to the x times 2 plus x. So very similar to previous part, but instead of e to the x times 1 plus x, here I have e to the x times 2 plus x. So solve for f double prime of x equals 0. That gives e to the x times 2 plus x equals 0. And again, e to the x exponentials are always positive. So that means 2 plus x equals 0. And that gives x equals minus 2. Again, then I can use the sign chart for f double prime to determine intervals of concave up, concave down. So x values here, minus 2 here, f double prime, and f. So again, you can easily see that before minus 2, you could use, for example, minus 3 as a test point, and you can easily verify that f double prime is negative there, and then positive here. F double prime negative means concave, f itself is concave downward, and f double prime positive means f itself is concave upward. So we can say f is concave downward on minus infinity to minus 2, and f is concave upward on minus 2 to infinity, right? Concave downward on this region, concave upward on this region. And what about the inflection point? Note that x equals minus 2 is an inflection point. Since the concavity changes at this point. Okay, guys, so today's lecture was straightforward. We gave recipes for intervals of increasing, decreasing for a function based on the sign of derivative, and a recipe for determining concave upward and downward based on the sign of the second derivative. Okay, guys. So that's all for today. So see you next time.